Alright, so in this video we're going to take a look at the different forces that act on vehicles, and this will be, I guess, the first sort of main topic when discussing vehicle dynamics. Now I should mention that this is by no means a comprehensive overview of all the forces. This is basically going through the most important ones, understanding what they are, how we can model them in a way that gives us some reasonable understanding of their behavior, and then moving on from there, because we're approaching this subject of electric vehicles from an electrical engineering point of view. A lot of it has to do with control of electric machines, and so it's important to understand vehicle dynamics, but it's not what we're going to spend most of the time discussing. So here we have a generic sort of situation where there's a vehicle and it seems to be going up some incline given by some degrees or some incline, I guess, angle alpha, let's say, and there are a bunch of forces acting on it, as you would expect, and we've labeled them here, but we'll define them shortly. So some forces, you have FD, for example, you have this mg sine theta, you have mg, of course, you have mg cos alpha, you have ft, you have this WF here, and this WR. There's some torque on these parts here. The TR and it's the TRR and the TRF, and so on. So there are a bunch of forces apparently, and we can label them. We can discuss what they are, and we'll discuss what they are in detail after. But we can kind of define them here, I guess. And we can say that Ft is the tractive force, and so this is the force that the engine or the motor of the vehicle produces to propel the vehicle forward. There is Fd, which is the aerodynamic drag, or sometimes it's called aerodynamic resistance. There is Fr, which is called the rolling resistance, and this is due to the fact that the wheels, or the tires, I should say, of the vehicle are not perfectly rigid, and they deform slightly when subjected to some weight, as all objects do. And then you have Fg, which is called the grade resistance, and this has to do with, and I can probably add here that this is sometimes called F alpha. So this has to do with the grade, or the incline, basically. So as this incline gets steeper, the component here, mg sine alpha, would obviously increase because alpha would increase, and you would essentially experience some resistance there. And then on top of these three forces, you have all the friction of the moving components, let's say, and all those internal losses, I guess. However, we're not going to deal with that, because usually those internal friction or transmission moving components, whatever you want to call them, those components are negligible compared to these three. So these three are what we're going to deal with the most, and these three are referred to as the resistive forces. And sometimes it's even called the road load sometimes. So if you see the word resistive forces or road load in the context of electric vehicles, this is what they're referring to. It's these three forces, and they have different behaviors, and they are modeled in different ways. And so we're going to spend some time now to look at how we can model these three forces reasonably accurately, I guess you can say, so that we can actually we can have some decent understanding of the way they operate. So let's start with the aerodynamic drag. So the aerodynamic drag, as you may already know, or you may have guessed, I guess, based on the name aerodynamic drag, has to do with the aerodynamic properties of the vehicle. So if you have a giant box, literally like a box with wheels, it's not very aerodynamic. But if you have a Formula 1 car, which is much more sleek, a lot more curved edges, lower to the ground, lower to the ground implies that it is a smaller cross-sectional area, then it is much more aerodynamic. So the larger I guess one way to simplify this is the larger the cross-sectional area of the vehicle that faces the wind, because that's the main thing that causes aerodynamic drag, the smaller that cross-sectional area is, the lower drag you would experience. However, there are two types of drag. So there is the internal aerodynamic drag, and then there's the external aerodynamic drag. And they say that this is approximately 10% of the total drag, and this is approximately 90% of the total drag. Now, this internal drag usually consists of ventilation, so like the internal air conditioning, cooling, heating systems, the ventilation that goes on in the inside and all that kind of stuff. So you can even say AC, heating, etc. And this external has to do with the air flowing, so the air flow around the vehicle. And of this external drag, they say that 10% is the normal resistance, and they say that 90% is, sorry, I got these numbers reversed. So this one is actually, so it's 90 for the first one, 10 for the second one. So it's 90 for the first one, 10 for the second one. So 90% is normal resistance, 10% is skin friction. Now again, these names or these terms are to just give you some context, but for the purpose of our analysis, we're going to simplify this, and we're going to say that that you can usually approximate the total drag by the external component. So we can approximate drag by external component. And there is an equation for that. So we can say mathematically, what is this equation? Because that's usually what we're concerned with when we want to model stuff, is how do we mathematically express this thing? So to mathematically express this thing, we say the drag force FD is equal to 1/2 rho AF times CD V minus VW squared SGN, which is the sine function, V minus VW. And this is the force in newtons. So what's what? This is air density around the vehicle, obviously, and this is usually 1.225 kilograms per meter cubed. This is the cross-sectional area, so I mentioned this earlier. So this is the cross-sectional area of the car, I guess. So I guess it's fair to say it's at the largest part of the vehicle. And this is taken in meters squared. This CD is the drag coefficient, we call it. Sometimes it's called the coefficient of dynamic resistance. It's easier to just call it the drag coefficient. And this drag coefficient is dimensionless. What else do we have? We have V. So this is the vehicle speed. And this is the wind speed. And finally, this is the sine function. So the sine function, you should probably know from mathematics. If you have the sine of x is equal to, if it's -1 or it's 1, it's one or the other, right? So it's either positive or it's negative, and it's negative when x is less than 0, and it's positive when x is greater than 0. So it basically shows you which direction the force should be acting in. So as you expect, I mean, the aerodynamic drag is dependent on the air density, it's dependent on the cross-sectional area, it's dependent on the drag coefficient, which is a property. I mean, you can there's ways to tabulate and measure that, basically. It's dependent on the wind speed, and it's dependent on the vehicle speed. Seems fairly reasonable and fairly logical. But one thing we should mention is that this is the wind speed. It's not just any wind speed, it's the wind speed, I guess, in the direction of motion. So if you think about the drag force for a second, the drag force opposes the vehicle's movement. So if the vehicle is driving, let's say, east, the drag would be let's say, going west. The force, I mean. So if the attractive force is going towards the east, the drag force goes towards the west. Now, the amount of drag that you experience is dependent on the speed, but you'll notice that the drag decreases as the wind speed increases, because we're saying that the wind speed is in the direction of motion. So it actually takes away from the drag, because it's kind of like running. If you imagine running against the wind, it's harder because there's more aerodynamic drag on you, I guess. If you're running with the wind, there's less drag because the wind it's in your favor, basically. So this is the aerodynamic drag force. Now, there is a sort of empirical way to approximate cross-sectional area. So you can say for vehicles weighing, what is it? I think it's 800, it's roughly 800 to 2,000 kilograms. And these are rough numbers, right? So like a lot of these things are empirical. So we say that AF is approximately equal to 1.6 plus 0.00056 m minus 765. So that seems like a very strange equation with no logical explanation as to where it comes from. It's most likely it comes from some empirical evidence of some curve fitting of some model that you can kind of say that this is usually the case whenever you have a bunch of vehicles that fall under this category. That should be AF. And this is the cross-sectional area, and we should define, I guess, M. This is the vehicle mass in kilograms. All right. Now, of course, if the wind is not blowing, so if let's say if your vehicle is somehow traveling in one dimension like this, and the wind is blowing like this, you can always decompose into the different components, of course, which is something trivial, I guess, at this point. So this would be VW, and this would be V, let's say. So you can always decompose this into two components, where it might be like one component is here and one component is here, and then you can find the one that opposes the direction of motion, and then go from there and do all these calculations. But for the most part, we won't deal with situations like that in any of the analysis we do in this set of videos. So you probably won't have to deal with anything along these lines. As far as the some behavior, let's say. Let's look at some behavior. So there is some impact. Let's talk about atmospheric conditions, because of course the atmospheric conditions around the vehicle have an impact on the vehicle. So atmospheric conditions affects, let's say, on FD. So there's a couple, again, these are like rules of thumb. You can kind of use the equations, and you can probably do these things. You can observe how certain changes impact the overall force. So you can say if we increase, increase temperature, and this is the ambient temperature, by 40%, results in decrease has an A before, so decreases FD by 14%. So if the temperature increases, the aerodynamic drag decreases. Now there's another one that says if you increase the temperature, I'll say temp, by, sorry, it's not temp, it's the altitude. The temperature was the other one. Increase the altitude by 1,200 meters. You basically reduce FD by 17%. That means that hot places that are very high up, you have much less aerodynamic drag, which is convenient. Although the issue is we all can't live in very hot places that are very high above sea level. Most of the tests we do in this type of work, we have some standard test conditions. So standard test conditions, sometimes abbreviated as STC, refers to an ambient temperature of 15 degrees Celsius and 101.3 kilopascals. So this temperature and pressure condition is what we denote as the standard test conditions. Next, we can look at the rolling resistance. So the rolling resistance, which we defined, or we denoted as, I believe it was FR, is a result of the fact that there is no such thing as a perfectly rigid tire. So if you imagine for a second you have some level or flat ground like this, and you have a tire on there, this is probably not a perfectly drawn tire, but if we were to zoom in on this section here, you would see that you would have the flat part like this, and the tire would not be perfectly, it wouldn't touch at a single point. There would be a sort of, and there would be a part where it would be kind of flat. Maybe I can use a different color there. So it would be flat like this at the bottom, and then it would go round along the top. Now the fact that this part at the bottom is flat creates a sort of distribution, I guess you can say, of forces like this, right? So what this does is there is now a force that acts opposite to this, to what would be here, I guess you can say, is the force of gravity, and that produces friction as this vehicle moves. Now the problem is, as this vehicle moves, this distribution also starts to change. So what you have is you have a rolling resistance, because as the tires roll, as the vehicle moves, you see that the distribution of this force changes. Therefore, you've added now some friction to the movement of the vehicle. So, long story short, this is, we can say tires are not perfectly, I guess there's a C in there somewhere, perfectly rigid. And that's what causes this. So they kind of flatten out here at the bottom, is what you should keep in mind. You can model this by, so we say mathematically, you can model this FR as mg cos alpha C0 plus C1 V squared. And again, we use the sine of V. But we haven't defined yet these things, but there are a couple of these parameters. So here, this parameter here, well, they don't really have names as far as I understand. It's just the overall thing is referred to as the rolling resistance coefficient, but the two of them define separate quantities. But this is the rolling resistance coefficient, and of course it's dimensionless, as you would imagine. And typically C0 is between 0.004 and 0.02, and C1, maybe we can squeeze this in here somewhere. So C1 is, we can say, well, I guess we should be consistent with that and write the same notation. So this is 1.6 times 10 to the minus 6, and 1.8 times 10 to the minus 8. Sorry, 1.8 times 10 to the minus 6. That wouldn't make sense. So it's 1.8 times 10 to the minus 6. And this does have units. Maybe we can squeeze that in there. This is s squared per meter squared. So this is seconds. Maybe we can just move that over rather than squeezing it all and making it look bad. So let's move it all over. And just rewrite that. So this is seconds squared per meter squared. So those are the units. And in most cases, this grade is very small. Alpha is referred to as the grade angle, as we discussed earlier. Well, we said it has some grade. We have to define the grade angle still. And this is usually very close to 1, so we can ignore that. And in a lot of cases, you can usually ignore C1. So CR is approximately, well, I didn't write CR, did I? So we can call this CR, is the sum of those two. So C0 maybe we can just define that here, I guess, rather than confuse. We can say that CR is defined as C0 plus C1V squared. So that whole thing is referred to as CR. And the sine function, as it was previously, is just the sine function. Now this force, we can kind of say, what is it? We said FR depends on, what does it depend on? So it depends on a bunch of things. It depends on a bunch of different factors, some that are obvious here in front of you and some that might not be. So one is that it depends on vehicle speed, of course, because you see that there's a V squared there. It depends on tire material. So the material of the tires, maybe put a space there because that's how we're supposed to write properly. Tire material and the structure. So the material and the physical properties of the tire. It depends on the temperature. So temperature. It depends on the tire pressure, or the tire air pressure, I should say. And it depends also on the road material. So that's what these parameters C0 and C1 are used to sort of quantify. And there are tables for these things, so there's no way, like you don't have an equation to calculate C0 and C1. You have tables for certain conditions that kind of estimate what this parameter should be given the conditions. So this is material and structure. Okay, so the next thing that we're going to move on to discuss is the grade resistance. And this one, I guess, is the most, well, actually, no, the aerodynamic resistance was fairly logical as well, but this is another one, maybe even more logical than the grade resistance. Basically, the grade resistance is a result of the fact that if you're going uphill, let's say, and let's say this angle is alpha, let's say this is your box, or whatever you are, let's say you're a vehicle, not a very nice vehicle, but you're a vehicle and you have some window, you have to take into account the fact that there is a component, well, we all know that from, I guess, high school physics, we all know that the force of gravity acts down, like this. We also know now that there is a component that acts down the ramp that way. So that component that acts down the ramp that way is what we refer to as Fg. And so, again, if you remember from high school physics, you know that Fg is defined as mg sine alpha. And alpha is this angle of elevation here. So alpha in most cases is usually small. So if alpha is small, then sine alpha just becomes alpha, and you can apply all of those approximations as well. But one thing we should do is we should define the grade, and the grade, when you might hear it said that, oh, it has a grade of 10% or it has a grade of 20%. So the grade, let's call it G, is defined as tan alpha. That's it, just tan alpha. And tan alpha is, I mean, if you have, well, I mean, tan alpha is relative to some measurement. So the measurement is this. So if you have an angle alpha, you have a distance x, and you have a height, let's say h. Basically, what the grade refers to is the increase in elevation. So the increase in elevation h, let's say, for every 100 meters that you've traveled. That's the sort of standard. So we can say here, increase in height by 100, well, I shouldn't say by 100, I should say for every 100. For every 100 meters traveled. For every 100 meters traveled. So let's say, for example, you have a grade, let's say if G equals 0.1, right? What that means is you traveled 100 meters and you went up 1 meter. Sorry, 10 meters, not 1 meter. That would be 1%. So you went up 10 meters. And that would give you whatever alpha you have. So we don't usually give the angle directly, because when you're dealing with vehicles, it's impossible to know what the angle is just by looking at it. But it's easier to understand how much of an elevation there was relative to your starting point. Now we can also define this percent G, I guess, which is called the percent grade, is defined then as 100 tan alpha. And I guess if we wanted to, we can say that this is 100 times h over x, because that's what if you assume this to be a right angle triangle up here, then you have opposite over adjacent would give you tan alpha. So these two equations here, I guess, that one, well, maybe we use a different color, this one here and this one here, are used to determine the grade. Now there's another fairly important measure when we deal with grades, and that's called the gradability. And the gradability, so the gradability of a vehicle refers to the maximum percent grade that a vehicle can climb at zero acceleration. That means there's no net force. So we can say, let's say max grade climbable at zero acceleration. Now I don't know if that's how you spell climbable. I want to say there should be another B in there. Maybe there is. Maybe somebody can leave that in like a comment below, or maybe we can correct that later. Climbable. Is that even a word? I don't know. I'll put a question mark there. Climbable? But basically, if you're at zero acceleration, let's say there's an alpha, and you're at zero acceleration. So basically what you're saying is the tractive force, Ft, should be equal to the Fg, basically, assuming all the other forces. Usually ignoring the other ones, because you want to see how good it is or how capable it is of counteracting the grade resistance. So why don't we mathematically then describe this? So we said that based on this, let's say ignoring Fr, Fd, and the acceleration dv by dt. You're not really ignoring it, but I guess you're just not considering it because it's part of the condition. You basically end up with this. You end up with Ft is approximately equal to Fg, which is what this diagram up here shows us, meaning that Ft is equal to mg sine alpha. Now we know from mathematics that tan alpha is equal to sine alpha over cos alpha, right? Then that means sine alpha is equal to tan alpha cos alpha. And we can apply our Pythagorean identities to say that sine alpha is equal to tan alpha. Well, let's go one step further instead of that. So let's get rid of tan alpha, and if you recall above, we defined tan alpha as g, and this will be the square root of 1 minus sine squared alpha, and that's the Pythagorean identity. So now what we can do is we can say that we can take this sine alpha and we can plug it into this mg sine alpha, and why don't we go ahead and do that here? So we can say Ft, well, sure, let's do that. Let's do it this way. So Ft is equal to mg sine, or mg times g times the square root of 1 minus sine squared alpha. But we said that Ft is equal to mg sine alpha, or you can just leave it all as you can leave it all in this form, I guess, whichever way you want to lead, whichever way you'd like to do that. But you can say this is equal to g times g times mg squared minus mg sine alpha. Maybe we can draw that after. All squared, like so. And of course we know that this is Ft here. So this is Ft. We know that this thing in here is also Ft. And how do we know that? We know that because of this here. So this part here tells us that Ft is from there, I guess. So if we have those two things that are true, then you can rewrite this entire expression as G is equal to Ft divided by mg squared minus Ft squared. And we refer to this as the gradability. And if you want to convert it to a percentage, you can say percent G. And I guess we can call this like some G prime or something like that. Let's call it like G prime, I guess, because it's not just any grade. Although it's still technically a grade, we can say percent G in this case would equal Ft divided by mg squared, all squared, that is, not just the G, minus Ft squared, and this just times 100. So this is the gradability in this case, and that is a measure of what did we say? The max grade climbable at 0 acceleration. So if you're operating just at the same amount of grade resistance, you can climb a certain angle. That angle is determined based on, essentially, it's a function of how much force you can exert and the weight of the vehicle. So we can go on and we can kind of summarize. Let's summarize, and we can say road load, I guess we called it, or whatever you want to call it. Road load, road resistance. We can say aka road resistance or resistive forces. So they're all referred to as the same, in the same way, or they're all referring to the same thing, I guess. Whether it's the road load resistance or the resistive forces, but you can summarize all of them, and you can call them F sub capital R, and that'll be Fd plus Fr plus minus Fg, and we can say here that plus is for uphill movement. So when you're moving uphill, the resistive force experiences a negative. And we'll discuss this in a second. And when it's negative when downhill. And now you might be confused, because if it's going uphill, why are you adding it? If it's going downhill, you're subtracting it. So you have to understand that forces are always relative, right? So if you're going up a hill like this and your vehicle is here, Fr is usually acting so as to oppose the tractive force. So if this is going this way, Ft, then your Fr is going this way. Now this sign, positive and negative, will depend on which way this vehicle is going. Because if it's going downhill, it's not resisting the movement of the vehicle anymore, right? So if this vehicle was going downhill, or if it's going uphill, that is what dictates whether it's a resistive force, because it has to oppose the motion. Now if the vehicle is moving downhill all of a sudden, so this is, let's say, uphill, right? So now if the vehicle is moving downhill, what you have is, if this is Ft and this is Fr, the grade resistance is now actually helping the vehicle move down. It's not a resistive force anymore. And that's why you would subtract it from the road load if it's going down. Whereas if it's going up, you would have to subtract it from the tractive force. So that sign, the plus minus with these two, with this note here, is what accounts for that fact, I guess you can say. So that's it as far as the forces are concerned. And I think this is a good point to stop this video, because in the next part what we'll do is we'll look at the equations of motion. So what we did here is we established all of the different forces that our vehicles are subjected to, or at least the key ones. And we have tractive force, aerodynamic drag, rolling resistance, grade resistance, and then we went on and we detailed all of them. There are some key equations here, some key concepts here. And in the next video, what we'll do is we'll look at the equations of motion. So if you have any questions, feel free to leave them in the comments below. Remember to like and subscribe to support the channel. And hope this was helpful, and we'll see you in the next one.